Alright, here goes nothing. This is the probably 6th attempt that I've made at recording this thing, so if I sound mildly annoyed, that's probably why. This whole transition to online classes thing sucks. But anyway, I hope you are all safe and healthy and enjoying the fact that you can now attend class, in pajama pants or no pants at all, as you wish. So, there's got to be an upside here, right? Alright, so let's get started on Chapter 6. In Chapter 5, we talked about working with two variables, both of which were categorical. We're going to extend that in Chapter 6 and work with two variables, one of which is categorical and one of which is continuous, quantitative variable. So this type of data is going to involve two groups where we measure something and try to determine if the two groups differ on the average value of whatever something we're measuring. So just like in Chapter 5, the first section is going to be how do we describe and generally deal with this type of data. The second section is going to be simulation-based inference on this type of data. And the third section will be theory-based inference on this type of data. All right, so let's get started with comparing two groups with quantitative responses. And the first thing we have to do is figure out how to describe this type of data, which means we're going to talk about something called the 5-number summary. And the 5-number summary is a really quick way to describe a distribution. It consists of the minimum, the lower quartile, the median, the upper quartile, and the maximum of a set of data. So going from lowest value to highest value. The lower quartile is the value at which, you have 25% of the data on one side and 75% of the data on the other side. Then comes the median, where you have half and half. And then the upper quartile is where you have 75% of the data less than that value and 25% of the data more than that value. So those 5 numbers are shown here, and it's worth noting that I have colored the bottom dot because it was much easier to plot that way. But in reality, the middle 3 dots probably are somewhere in that column rather than at the bottom. So, but all the dots have the same value, so it's equivalent. All right. So you can kind of see how this divides our data set up into fourths that are all of about equal size. The distance between the lower quartile and the upper quartile is called the interquartile range, or IQR. And the IQR is another measure of variability, like the standard deviation. The difference is that the IQR is what we call robust to outliers, in that we have this outlier at 21. Even if that outlier were 101 instead of 21, the interquartile range would not change. So the specific value of the lowest and highest parts of the distribution doesn't matter. It's just the ordering and the ranks of each data point that matter. All right, so a visual way to represent the 5-number summary is with something called a box plot. And I'm going to very quickly describe in words what box plots are, but it'll be a lot easier just to draw it out. So we draw a rectangle with the sides of the rectangle at the 25th and 75th percentile. So lower quartile, upper quartile. We draw a line through that box corresponding to the median. Okay, so we've accounted for half of our data thus far. Then there are what are sometimes called whiskers, and box plots are sometimes called box and whisker plots because these lines extend outward from the box like whiskers on a cat. There are a couple variations for box plots. The simplest is you draw a whisker from the edge of the box to the smallest value and from the upper edge of the box to the largest value, and you call it good. Sometimes it's more informative to draw whiskers in such a way that we can identify outliers easily. And so what we do then is we declare anything that's outside of 1.5 times the interquartile range distance away from the box as an outlier. The whiskers extend to the furthest away not outlier point, and then the outliers are shown with dots. Now what this lets us do is to visually identify, hey, these observations are outliers. They may be problematic for different statistical analyses. Or, hey, watch out for this, or go check and see how that point was recorded because something may have gone wrong. So visually highlighting the outliers is a generally useful thing. And that's why that particular variation on a box plot or box and whisker plot is the most common variation. All right, so enough talk. Let's make a box plot for our data. Easy stuff first. We can fill in the quartiles and the median and draw our box. So our lower quartile is 7, our upper quartile is 12, our median is 9. From that, we can calculate the interquartile range. So 12 minus 7 is 5. And we can just scribble down 1.5 times the interquartile range is 7.5. So our whiskers can be at most 7.5 units away from either side of our box. All right. Next, we subtract the interquartile range from the lower quartile. We add the interquartile range to the upper quartile. And then we take the least extreme value between the edges of our whiskers and the data. So if our whiskers extend past the range of the data, we stop where the data stops. Okay? So if we do the computation for the bottom whisker, we would take 7, which is our lower quartile. We'd subtract 7.5. That's 1.5 times the interquartile range, and get negative 1/2. Our data stops at 3, so our bottom whisker stops at 3. Okay, because 3 is larger than negative 1/2. For the top whisker, we add 7.5 to 12 to get 19.5. Our data extends to 21, so the least extreme value is that 19.5, and that's where our whisker stops. By that metric, we have an outlier at 21, so we draw a dot there. And that helps us to see, hey, there's this one point that's maybe a little bit odd. All right? So the nice thing about box plots is that we can easily compare distributions of different groups. We can say that the distribution of number of cases of hepatitis B in California between 2000 and 2018, so this is annual cases, it's pretty symmetric. It's, maybe like 260, and never gets beyond, never is less than 210-ish or more than 320-ish. That's pretty easy to say from this. We can say that in general, there are usually fewer measles cases than hepatitis cases. Either hepatitis, I guess. But in a couple of years, we had some outliers that might have been indicative of measles epidemics that got out of control, perhaps. People not vaccinating and measles getting into unvaccinated communities and spreading like wildfire. I think that happened last year. So we can say that the distribution of measles cases is usually well under 50-ish. Definitely under 100 unless we get one of those really broad spreading events. But take a look at the box plot for mumps cases. There we have a bottom whisker that is really, really short. The lower quartile is also really close to the end of that bottom whisker. So our data is really compressed at the lower end of the scale. Our median's not that much higher than that, so we've got 50% of the data in a tiny little range, and the other 50% of the data is spread out over almost 300 cases. So we've got a tiny range and then a really, really, really big range for the two halves of our data. So what this is indicating is that we have a very skewed distribution here. We've got half the distribution concentrated in a small area and the rest of it spread out over a huge range. So that is one of the nice things about box plots, is that it makes it very easy to compare distributions. All right, so I found a really cool data set that I was really excited to practice in class, give you a chance to draw box plots. I recorded a walkthrough of this exercise and constructing these box plots on my tablet so that I could draw. And I've posted that separately, but I'd encourage you to take some time and draw out the box plots yourself. There's some graph paper here for your convenience if you've printed the slides out. I'd also encourage you to check out, there's some pretty cool animations in here. They went through and measured all of the different pocket sizes in 40 different pairs of women's jeans and 40 different pairs of men's jeans. And you can see from the visual here that women's pockets are pathetic. I think they started collecting this data with that idea in mind, but I don't know of anybody that would contradict the bald-faced assertion that women's pockets are pathetically small. But there are all sorts of different visualizations of this data that are fun to check out, including which phones fit in which pockets, what objects you can safely fit into a pocket, and that sort of thing. So that could be good for some amusement if you are bored and want to read through that. But I do encourage you to draw out the box plots and then go watch the video and check your answers. At this point, you should be thinking about working through Exploration 6.1. You can work in your groups on Canvas. Each group has a separate group discussion board. If you want to work in your groups, or if you want to form new groups, let me know and I will make you a Canvas group to work with each other on. But if you want to submit the assignment alone, that's fine too. However you learn best and whatever is easiest for the situation you've got right now. So you need to complete at least problems 1 through 13, and there's some extra credit in it if you work through the last 5 problems that go through other further analyses on the same data. All right, so I'm hoping to finish recording the rest of the Chapter 6 lectures later this afternoon so that those can all get posted. I know that you are all, I'm recording this on Tuesday of spring break, so in about a week you guys will be taking exam 2. I'm sure that nobody's thinking about Chapter 6 before exam 2 happens, so I'm hoping that I'll have all the lectures up by the time you get to the point where you're thinking about Chapter 6. So, alrighty, thanks.